the similar features. So we don't have to do redundant things. All right. And speaking of optimization, right here, I have made the graph using 1, 2, 3, 4, 6 clusters, but I don't actually know if this is the optimized number of clusters. It can be like 2, 3, 5, 6, 8. It has some things we have to consider. So like computational power, for example, or time it takes, or like if it actually makes sense to do each number. So how do we do that? We use inertia, and I'm going to talk about it. So for each centroid, all right, these are centroids. So we're going to do the sum of mean squared. So we square the distance between each data and the distance between the centroids. We square them, we sum them together, and we square root them. The reason we square and not do the the absolute, we not the absolute, is because we want to penalize things that far away from the centroid, and we want to emphasize things that are close to the centroids. It's a bit technical, but stay with me. It's gonna make sense later. So yeah, and the reason we have to square them is because we don't want to cancel out the negative values. Okay, so before last night, when I thought about this concept, I think we can just use the second derivative of the graph. All right, so for the calculation of, let's say this is 6 centers, right? We have 6 cluster, and we calculate the inertia for this 6 cluster. We can plot the graph that looks something like, excuse me. Okay. So we have this, all right, and this will be the number of clusters, all right, and this will be the inertia. So when the number of cluster increases, the inertia will decrease, something like this. But so it's a function, right? So we can find derivative, and we can find the second derivative to see the point where the rate of change change the most, and then we can use that to, okay, this is the optimal point. But last night I tried to actually code it myself, and it doesn't work, so I just changed it to be just the mean, not the second derivative. So right here, we have the first point, this is 0, and 0 is 1 cluster, right? And we have 2 cluster, 3, and so on. And this is the number of, the value of inertia. So right here we have the first, second, third, fourth, sixth, seventh number of cluster, and the value is around like 30. So this is the optimized value that I calculated using the data I implemented. I'm going to show you. All right, so we have this 305 list of paragraphs that I extracted from the internet. So it's a lot of information, and we have to clean it. All right, this is the first step, is to clean it. So don't look at the code, it's gibberish, but I'm just going to show you for the sake of completion. So we have some modules, all right, lots of them. I'm going to use everything, and we import things, we drop the duplicates, and that's our data. Right here, yeah, just like everyone said, I have stop words right here. I made this function to lemmatize them, and I remove punctuation, all right, and I also remove stop words, and store everything in my data frame, just so that I can work with them. So now we have this, from 300 rows, we reduced to 241 because of the duplication. And then I made the holy list to do back-of-words. All right. The method I choose is back-of-words. So I think we are familiar with this. the basic idea is we have long list of a vector, long vector of words, right? And we compute if for each document we have word in that backup word. So 0 represents there's no word yet, and 1 represents that there is. So we have this document term matrix that someone said before, and this is something valuable. Okay, all right, we're going to use this data to actually compute something. So because it's a very multi-dimensional data, we have to compress them. I choose PCA to compress things. So I made another data frame and compress everything just to reduce it to PC1 and PC2. So only 2 dimensions, just so that we can visualize them. And this is the final data. We have the X and Y axis represent PC1 and PC2. And yeah, now it's just not cluster, it's just one chunk of data. We're gonna go further. So now this is my method that I propose. So when we want to compute for the optimized number of cluster, we find we sum the list of all inertia in my list. So we have list of inertia, right, for every cluster, and we divide them by its length. So the average, the mean, and then we find the point where it closest to that mean. So going to this graph, the mean is like around 30. So after I do the calculation, I choose this point to be the number of optimized number of cluster. So it's around like 7, and then I construct what is this? Oh, the scatter plot, of course. Yeah, with the number of 7 cluster. So it should be 7. Yep, 7 cluster. And as you can see, it doesn't like mix together, like badly mixed together, but it doesn't like farther separated. So it's just like sweet spot in the middle, should I say? Okay. And the reason we have to do this complicated stuff is because when the number of data gets increased intensively, it's going to be computationally intensive for computers. So when we have to decide to look on a graph, like if we take a look, it's very hard to see which point we're going to take for optimal point, right? So if we do the calculation, we can just, all right, this is a standardized way to select the point. So that's what I think it's very cool about this thing. Okay, and we're going to actually take a look at the result of one cluster, right? That is way above. So we have some points here, data points. It looks scattered, but this is the cluster number 3, I reckon. Okay, and this is the result of the words in each document that contains in the cluster number 3. And as you can see, there are lots of words about dog and like walking outside and taking activities, stuff like that. It's gonna go together. So from this project, it doesn't like have specific purpose. I just want to emphasize on the thing that we have another cool way to select the optimal points for cluster number. But of course, when we classify things, it's a classification problem. We can do many things usually, right? We can cluster the tweet, of course. Okay, and that's about it. Thank you. Questions?
Any question? So, what is the difference between this and elbow approach?
Yes, it's the elbow method, but the elbow method we use our eyes, right? To this could be the elbow, maybe this, and we can like have different decision. But when let's say if we can standardize this method, we can like okay, this is the actual elbow, and we're gonna use this point, and it works for every number of the entry we have. Let's say I have like the number of, k, right? I have k from 2 to 40, and it works for every cluster we want to try. So it's I mean refined approach of elbow method, I would say.
Okay. So elbow method, that's what I think. Maybe elbow method with second derivative, elbow, to determine elbow, you can use second derivative. Right?
Yes, because I tried to code that last night, but let me draw a graph again. So let's say I have this elbow, right? When I use second derivative, the points it usually be like right here or like right here. So it doesn't like go to the elbow, and that's very weird. And I try and I mean I actually code that the entire night, and so it didn't work. So I guess my theory is wrong. I mean it's okay to be wrong. So I just okay, let's try something simple. Maybe average could work. So I tried the average and it worked. It falls around this point. So that looks like the optimal point. So okay, I just changed from the second derivative to the average, and that works a lot better. And it's much more simple. We don't have to like do the curve fitting thing because that would be computational intensive.
What I thought, maybe it's a good idea that maybe you can take two sample, suppose what you can say, representative points, and then represent it as a set of lines, correct? So derivative is a slope, okay? Now you have small line segments, and the change in, then you take a next derivative as a difference in that slope. That should be the elbow point, right?
Yeah, that's my first thought, because I've been thinking about this for like 2 months. So when it's very interesting because it didn't work as I thought. So when we have this, the first derivative is gonna be like, so this is like exponential curve. So the derivative is gonna be still exponential. It's gonna be steeper, and the second derivative, it was also much like steeper like this. And when it takes this point, it turns out to be like.
Any other presenter? Is there anyone who is presenting after this? Okay.
Yeah,
No
take
presenter.
one hand, sorry.
Okay, no, I'm just checking whether we can take more time.
Yeah.
No presenter, right? Okay, so this is your last presenter, you have 10 minutes.
Okay, so it didn't work as I thought, and I've kind of failed a little bit like failed, but I just changed to be the average instead. So that's what I thought.
Okay, good. Any question? Anyone else? Okay, wonderful. Thank you.